planar. If there are too many edges and too few vertices, then some of the edges will need to intersect. The smallest graph where this happens is K5. And K5, which I'll draw, looks something like this. There we go. If you try to redraw this without edges crossing, you quickly get into trouble. There seems to be one edge too many. In fact, we can prove that no matter how you draw it, K5 will always have edges crossing. So here's a theorem that we can prove that K5 is not planar. Well, we're actually going to prove this. The proof is pretty fun. It's by contradiction. So let's assume that K5 is planar. So assume K5 is planar. Well, then the graph must satisfy Euler's formula for planar graphs. So K5 has 5 vertices and 10 edges, so we get that 5 vertices minus 10 edges plus the number of faces should be 2. Which says that if the graph is drawn without any edges crossing, there would be 7 faces. Now consider how many edges surround each face. Each face must be surrounded by at least 3 edges. Let's let B be the total number of boundaries around all the faces in the graph. So this is going to be specifically the total number of edges, and I spelled edges wrong, edges, total number of boundaries specifically, or I should say boundaries, my bad, not edges. Total number of boundaries around all the faces in the graph. Thus, we must have that 3 times the number of faces is a lower bound on B, but also we know that B should be 2 times the number of edges since each edge is used as a boundary exactly twice in planar graphs. Putting this together, we get that, and let me make myself a little bit more room here. If 3f is less than or equal to b, and b is 2e, that means 3f is less than or equal to 2e. But this is impossible since we've already determined that f is 7 and e is 10. And that would mean that 21 is less than or equal to 20. No, it's not. This is a contradiction. So, in fact, K5 is not planar. The other simplest graph, which is not planar, is K33. Let's try to prove that K33 is not planar. And to do that, we're going to prove by contradiction again. Now, let's suppose that K33 is planar. So then by Euler's formula, there will be 5 faces since there are 6 vertices and 9 edges. And by Euler's formula, that means 6 minus 9 plus f equals 2. And so f is 5. So how many boundaries surround these 5 faces? Let's let b be that number. I'm going to try to spell this right. Boundaries. I think that's right. Since each edge is used as a boundary twice, we know that b equals 2e. And so also, we know that b has to be at least 4f, since each face is surrounded by 4 or more boundaries. We know this is true because K33 is bipartite, so it does not contain any 3-edge cycles. Thus, we know that 4f is less than or equal to 2e. But this would say that 20 is less than or equal to 18, which is clearly false. Thus, K33 is not planar. Note the similarities and differences in these proofs. Both are proofs by contradiction, and both start with using Euler's formula to derive the supposed number of faces in the graph. Then we find a relationship between the number of faces and the number of edges based on how many edges surround each face. This is the only difference. In the proof for K5, we had that 3f was less than or equal to 2e, and for K33, we found that 4f was less than or equal to 2e. The coefficient of f is the key. It is the smallest number of edges which could surround any face. If some number of edges surround a face, then these edges form a cycle. So that number is the size of the smallest cycle in the graph. In general, we let g, lowercase g, be the size of the smallest cycle in a graph. G stands for the girth, which is the technical term for this. And just for the sake of showing you, that's what a g looks like. Then for any planar graph, we have that g times the number of faces is at most 2e, which is the number of boundaries here. When this disagrees with Euler's formula, we know for sure that the graph cannot be planar. So this is a great strategy for showing that graphs are not planar. Anyways, thanks everyone, and I'll see you in the next lecture.